section 13.4, double integrals with over region R with polar coordinates. Okay, and so the reality is, let's just kind of look at something with the origin here, and let's look at kind of two dimensions. Let's come out this way, and if I've got curve going through here, first of all, remember polar coordinates, we're doing like f of r theta is what we have. So we're r theta, so r is how far out we are. Okay, so this could be like this first one could be like r equals a, so like a kind of a radius. So this is r equals a would be the first one. The second one out here, you know, that's part of a circle here with radius, we'll call it r equals b. So that's how far out away from the origin we are. And then of course we have angles as well. So just kind of remember that. If we have this first theta is theta equals alpha. Okay, so we're gonna use alpha for that angle, and then going to this one, this is gonna be beta. So we have theta equals, this maybe theta 1, theta 2 is beta, where I should probably call this R1 and R2, doesn't really matter. But the first radius out there is a fixed constant A, second radius fixed constant B. And then what we're doing is we're looking in between, right? And so we've got different things here. And what we're gonna do is we're gonna split these up. We're going to split these up, and ultimately what ends up happening when we have, you know, partitions here, let's just look at one of them. One of them is going to look like this. I'm going to blow one up here. Let's say this is kind of the biggest one, but it's kind of a curved rectangle is what it is. And then we have a point in there, which is we're kind of use that as the midpoint. And the way they use this point as the midpoint, they're going to call it like, well, it happened already. It's not letting me write. Oh my gosh. So apparently I didn't fix the problem. We're going to have to start meeting. So you two can talk amongst yourselves of what's a good time to physically meet. I don't know what to tell you, but this is killing me. So I gotta go out and come back in.
What's up, Schwab?
Hey, yeah, I don't know when we'd meet.
I don't either.
I have no.
I'm gonna look at my schedule, like if it could be in the day. When do you have a study hall?
I have study hall 4th period. You have it 3rd, you said.
Sounds right. No, I have it 4th.
You have 4th too?
Yeah.
Okay.
You both have 4th period study hall?
Yeah, I have PE though. So it's PE study hall, not just study hall.
And I don't know what that means.
So some days I don't have study hall, and some days I have PE. I don't know what days I have PE though. Let me see here.
Maybe it's just every other day, Schwabby.
No, it's weird.
Is it?
I haven't had PE since for like 40 years.
We're gonna have all right, so that's really kind of when we want to focus on. I can also potentially do Tuesday, Thursdays at like, you know, before school starts, but you know, I don't know if you want to do that or not. I want to avoid it if we can work something out during the day. But anyway, we're just gonna pick a midpoint in there. So this is a curved rectangle, really. And so we're going to go halfway between the R's, and we're going to go halfway. So this is the ith rectangle here. And of course we can look at, you delta sub I of A is kind of the area of that, right? And then what this is a sector where we have area of a sector. Do you remember that formula? So area of a sector would be, let's see, area of a circle is pi r squared, right? And then this is a portion of the circle based on how much of the circle you have, and you got an inner and outer circle. But anyway, it's the area of a sector is like 1/2 radius squared times the theta angle, I believe. Does that make sense? I looked it up. We went over it. Do you remember going over that area of a sector? We figured out one day in class. You don't remember that, do you? It's okay to keep your sound on. It's just you two.
I do not remember what the area of a sector is.
Yeah, I also do not. I remember going over it, but I do not remember what it is.
Okay. Well, it's area of a sector is 1/2 r squared times theta. So we kind of look at that. I mean, you got the outer and inner one. Anyway, they end up developing the double integral formula with polar coordinates. So anyway, but they're using this. So really what I'm doing here is I'm looking at one of these curved things. They look at a Riemann sum, and what they do is they're going to look at the longest diagonal. And so they're going to let the norm of the partition for the ith curved rectangle go to 0, where the norm of the partition is the longest diagonal. Okay. And then we're going to have more and more and more of these with smaller and smaller and smaller kind of area, right? And we're going to let that go to 0. It ends up being a Riemann sum. But let me just, since you say you don't remember, let's see if we can figure it out quick. But if I have a circle and I want a certain sector area, right? Well, basically, what's the area of the whole circle? That'd be in black. The area of the whole circle is pi r squared, right? And so what's the area of the purple part of it? That is a sector. Well, basically, it's going to be proportionate. So the area of the sector is going to be whatever portion of the circle it is. Okay, so there's 2 pi overall is the whole circle, right? And so out of this, it's the portion, it's theta radians divided by 2 pi, right? So if this is in radians, so we got the radian measure here, and so we're going to call this angle theta in there. So that's theta. So let's just say that kind of looks like 30 degrees or pi over 6. So let's say that's pi over 6. Well, the whole thing is 2 pi, right? So pi over 6 out of 2 pi, but then times that's the proportion of the circle that we have, and the whole circle would be pi r squared, right? For the area of the whole thing, and we just want this part of it. So what happens here? What happens is the pi's cancel, right? And we end up with area of a sector to be equivalent to what? 1/2 r squared theta. So do you remember that now? We actually weren't really sure where that came from, but we figured it out one time. And then what are they doing? So what's the book doing? The book has really 2 circles, right? So we have a bigger unit here. So this was the black one was out at A, R equals A, and this is R equals B out here, and we're looking in here for that part, right? So anyway, that's kind of what they're doing. I'm on page 1102. So anyway, that just kind of gives you gives you that. So they develop some of this stuff. But anyway, what we're going to end up with is a Riemann sum, and we're going to have a, let's see what color I'm on. We're going to have a double integral over region R of f of r theta dA. Okay. But what happens is dA in polar coordinates is going to be r dr d theta. So this is one thing that you're going to want to know in polar coordinates. The dA is r dr d theta. And so what we're going to have then is the double angle. So we have with respect to r and with respect to theta. So this, what we end up having, excuse me, so I've got f of r theta, and then r, if I'm doing the dr first, so remember I kind of said, hey, the inside one, you're kind of doing that first, right? So if I'm doing the with respect to r first, well, what's r range from? R ranges from A to B, right? So that would be A to B right here, according to our picture, right? That was actually in blue, sorry, in my previous picture. And then if I have d theta after that, r dr d theta, let me go to black. D theta, what was theta going from? Theta goes from alpha to beta, right? So do that. So basically that was the picture that we had, but the r dr d theta is what our dA is here. So this is kind of easy way to remember it. Now we could write it the other way where we take the antiderivative with respect to theta first. So let me just clear this off and say if we did that, what would our double integral look like? If we have double integral of f of r theta times r, but instead of dr, let's do d theta first, and let's do that. And what would that be? Theta goes from alpha to beta, right? On that picture I was drawing before. And then if we go dr after that, we're going to go from A to B. And so once again, that was the picture that we had where we have r, in this case being the blue, r goes from r equals A to r equals B, and the theta goes from alpha right here for that one, and beta is starting out at the positive x-axis going up beta. So we got theta equals alpha, theta equals beta there, and then we're trying to come up doing that stuff here. All right, so a couple of things. There's some nice applications from this. One thing that could be used is if f is a function that's on or above this when we go into 3 dimensions, this could actually be considered like volume, right? So depending on what that surface is, but let's kind of back it off before that and go, let's just look at area. I think I can do area. Let's see. Well, the book in this section doesn't do a very good job, I don't think, of describing a difference between area and volume. So we're going to kind of learn by seeing those things. But let's just go. If I have, I'm going to switch my color, but if I have z being my height is f of r theta. Okay, so I got 3 dimensions now. Anyway, and I have, so once again, let's see, what did we have? We had kind of coming out here like this, and then we had r equals A, r equals B, right? Going from A to B. This is in quadrant 1, right? So everything's positive, or octant 1. And then we had I think the thetas were alpha to beta, right? Right there. So we kind of had this, we had this region right here, right? This is the region, the kind of the sector region that we had, that's on the table surface, right? So basically what I had drawn before with the slanted rectangles is on the table surface, right? And then if we have a surface, f of r theta to be the height, let's just say it's something up here, okay? Then what do I really have up here? Then basically, if I can draw this kind of to scale, what I end up having, if this is the same type of shape up here, like I take a tiny rectangle out of there, slanted rectangle, and then go up, I end up with volume of that thing, right? So what is the volume of something that has a sheet of f of r theta for a height that's entirely on or above the table surface? Would be the double integral over region R of f of r theta. And instead of dA, remember it's r dr d theta, or unless you'd rather switch and do r d theta dr, depending on how you're going to do it, right? So anyway, this is a representation of volume in polar coordinates, just like we had a representation of volume in rectangular coordinates in chapter 13.2. Now we're in 13.3. So let's look at a couple examples. And then we're also going to be able to do area when we're only in 2 dimensions with that. But there's quite a few things that we're going to skip in here in 13.4 because it refers back to 13.3. So do you both have your books available?
Yeah.
Yes.
Okay. So now on page 1104, and you see the blue box is what I just covered, right? So we used a Riemann sum there to come up with volume of that shape. So let's look through example 1, and then we're gonna be skipping a bunch of examples because I didn't cover them. All right, so let's just kind of look at example 1 here. Go through this. It says find the volume of the solid in the first octant bounded by the cone z equals r. So z equals r, that's a cone, and then a cylinder, r equals 3 sine theta. So we kind of have to remember we did all that stuff. Was that chapter 10 we were doing a bunch of this stuff? Do you remember? I don't think it was chapter 9. I think it was, maybe it was chapter 9. It was chapter 9 and 10, I think. Anyway, but r equals 3 sine theta, which way does that go? Does that go out the x-axis or up the y-axis? Do you remember? It doesn't really. It goes up, doesn't it? And the cosine is to the right. Do you remember anybody remember what chapter that was?
Was it 9?
I
think it was 9. Which is actually way back to Calc 2. So the good thing is, you know, we have to remember Calc 2 to do Calc 3. I was trying to look back on that. We had, can't remember if it was 9-6 that had, no, that was length of arc. But we had some nice, oh, there it is. Yeah, the cosine theta is to the right, and the sine theta is up on top. And if we had minus some constant times sine theta, it'd be down below. But anyway, and then the radius, let's see, 3, 6. So it goes up to 3. Anyway, but up was normally to the y, right? So we were doing this in 2 dimensions, right? And so that's the table surface. So this is a, what'd they call this? They called this a cylinder. And so it's combining a lot of things here, but the reality is it was a circle with diameter of 3 going like if I had the XY axis here, it looked like this. No, stop it. It was on the top. And I get to erase that. That was horrible. Let me go back. All right. Anyway, it was this, right? Remember that? And I think it was up at 3 here. So the radius was actually 1.5, right? Anyway, so take that, turn it, it's this way. So we got 1.5 is right there is the middle. But anyway, what happens, then Z is unrestricted for this thing, right? So what happens is we also have that up here. We also have it down below, but we end up with a cylinder that's sitting with the Z axis is actually, you know, attached to the left side of it and it's out to the right. Does that make sense for the cylinder? Hopefully.
Yeah.
Okay.
Yeah, it does.
Perfect. And then I'm going to use a different color. Let's use something pretty. I like purple today, or plum. But anyway, Z equals R. Z equals R is a cone, and we're bounded in the first octant. But basically, what theta can be anything it wants, right? And so if the height is, anyway, I don't know. So it's just something like that. And it's trying to find the volume of this bounded in the first octant. So something like that. You know, but I am cutting, by the way, and I'll use a different color here. The ZY axis bounds the back side of this, so it cuts it off, and it can't be, like, we're not doing the back side of the pop can. So if you cut that pop can in half, actually this goes behind, so that the ZY axis cuts this can in half, doesn't it? So we're not doing the back side of the can because I'm bounded by the first octant. It says, and of course, I'm also bounded on this side, right? But there isn't anything like left of the ZX plane, correct? There's no negative Y values. So in other words, it does not go back this way, right? Anyway, and then of course, we don't need to worry about negative Z values either because even though the cylinder would keep going downward, it doesn't matter because I'm blocked by the table surface, which is the XY plane, right? So anyway, that's kind of what we're trying to figure out the volume of on this example. So let's just step through it. So ultimately, you know, everybody can read the examples just like I can, but I want to make sure that we follow what we're trying to do, what it might look like, etc. And so the volume is going to be the double integral over surface R of what? F of R theta times R dr d theta. Once again, critical that you remember that dA in polar coordinates is R dr d theta. Didn't really go into the theory of why that's the case, but the book does explain that. And then of course, what's F of R theta? In this case, F of R theta is your Z, right? And Z equals R. Okay, so that was the purple one. But anyway, so this is R times the R dr d theta. Whoops, trying to go back to black. Times R dr d theta. And then I'm going to want, you know, the double integral of that. Of course, so that, where do they get now? That's where they get the R squared. So this is just R squared now. And then what does the R's go from? Well, basically when I'm looking at that picture, right? How far out can I go? Whoa, I can't see that. But anyway, the R can go from the other equation was given by, this, where we got that. Anyway, was R equals 3 sine theta, right? So it starts at 0, goes out to 3 sine theta. So 0 to 3 sine theta would be what R can range from. So that's the dr. And then we would do that first. And then what's the theta go from? Well, if I'm going to be in octant 1, theta is just right here, right? So it goes from 0 to what? To pi over 2 is halfway up. So anyway, 0 to pi over 2 would be the second one. Sorry, I didn't really want green there, but I guess I do want green. So I'm doing the first one first. I should have picked a different color there, I guess. Anyway, and then the d theta was in green. Okay, so long story short, pretty easy to take the antiderivative of r squared with respect to r. It's r cubed over 3. Evaluate it from 0 to 3 sine theta. And then plugging 3 sine theta in, what do we get? We get 27 sine cubed theta, which is not very fun to take an antiderivative of. But since the book does it for us, we're going to go 0 to pi over 2 and 27 over 3 is 9, right? So I'm going to pull that 9 out front, and then sine cubed theta, d theta. So what I tried to do is on the ones that I'm going to have you turn in is I'm trying to make your life easy and not have all these trig integrals. Okay. They just give the answer to this, but we spent a lot of time doing trig substitution integrals back in Calc 2, right? So, and if you're like me, that wasn't a whole lot of fun. You need to go back, look it up, remember the process, all that type of stuff. Anyway, so they go ahead and calculate what this is, but I think they wrote this as sine theta times sine squared theta, which is 1 minus cosine squared theta, and then split it up into 2 different integrals, et cetera, that way. And long story short, and then you evaluate it from 0 to pi over 2, take it times 9, you get 6. So 6 cubic units would actually be that volume. So I'll kind of skip to the chase on there, but you can go ahead and finish this out or go back and verify the book is right on that. So I've tried to eliminate awkward antiderivatives for you, being your friendly co-host of the independent study. All good with that? All in favor? Say aye.
Aye.
Hi.
Jordan's like, give me the hard ones. Just give me the hard ones. All right. Anyway, and yeah, I'm the same way. That's what, people ask me, like, they're taking Calc 2, don't tell them, but Calc 2 is great. We do a lot of different antiderivatives and stuff like that, but like, it's just sometimes it's just grudging work, right? Like, I prefer to stick with the fun stuff. Just because you can do those trig integrals, right, doesn't mean I want to sit there and occupy my time with them.
I thought Calc 2 was the worst out of all 3.
Yeah, well,
I agree.
Your professor probably had a bad attitude, because I'm the same way. Anyway, so example 2 on page 1104. Sorry, assuming how come it's not letting me draw there? Yeah, example 2 we're going to skip. That's section 13.3. Example 3 we're going to skip because these are section 13.3, which we skipped. And so we're moving on. Look how quick we're going. Now we're to example 4 already on page 1106. All right. So let's look at that, example 4. And this is, like I said, it didn't really give a very nice example at all, but it's saying find by double integration the area of the region enclosed by one leaf of the rose R equals sine 3 theta. And if you remember, once again, we got to go back to chapter 9. We got to reference a lot of chapter 9 here, which is okay. But we spent a lot of time on that. But how many leaves are there on sine 3 theta? Was there 3? You remember?
Yeah,
Nice.
I think so.
And how did we come up with that quickly and easily? We said, hey, sine of 3 theta. Well, normally I go out to 2 pi, but I got to have, you know, whatever times 3 is 2 pi. So it's 2 pi over 3 is 1 period, right? So you take it, if it got sine of n pi, so if I have sine of n pi, then the period, not n pi, n theta, dork, the period is going to be 2 pi divided by n, right? Anyway, so we have, you know, we have that. And then what happens is it repeats itself twice to get to 2 pi. So out to the right is 2 pi. I don't want to duplicate that. Stop it. What? Did that move for you? That's horrible. It moved for me. Like it looks different. Come on. Anyway, I'll just redraw that. So this was 2 pi over 3, and then we got 2 more. So that's 4 pi over 3 is 2 of them, and then 1 more should be 6 pi over 3, but what's that? 6 pi over 3 is 2 pi, right? 6 pi over 3 is 2 pi. Anyway, so it's 2 pi over 3 gives 1 full cycle. Anyway, that ends up giving 3 leaves is what it gives. It shows it on figure 7. We don't need to go through all that, but if I want the area of one of those leaves, and we went through kind of, you know, a lot of this, but I want this area here. The question is, how do I come up with that area? Well, the area is going to be basically a double integral formula, and it doesn't do a very good job on this, but it's just going to be, we don't have heights on this, so there's no volume. So your function really is just 1 and then dA. So it's the double integral of dA. But what's dA when we have polar coordinates like this? It is, instead of dA, we said it was r dr d theta, right? Man, stop. R dr d theta. And then, so what am I going to do? I got to figure out where I go from. So it's just the double integral of r dr d theta. So which one do I do first? I am doing the r. What's r range from? Well, on this example 4, we said r equals 3 sine theta, right? So we start at 0. Sine of 0 is 0, right? So 1 leaf, we get to, well, we go sine 3 theta here. And then what's the theta go from? Like, what does one, let's see. Well, 2 pi over 3 is a full rotation, right? Let's see. What gets us back to 0? So they only go to, they go to pi over 3. So we do, so this is going to be your big challenge here, is trying to come up with what are the limits of integration here and here, right? And so if I start at 0, then halfway here is pi over 3. Question is, where does that take me? So I go out to 1. This has a height of 1, right? At what? Half of that, which is half of pi over 3 is pi over 6, right? Sine of pi over 6. No, this is what? It's not. I wrote this wrong, everyone. Did anybody notice that? It's not 3 sine theta. It's sine of 3 theta. Sorry, let me rewrite that. Sine of 3 theta. Anyway, and the sine of what is 1? Anyone?
Pi over 2.
Pi over 2, right? And 3 times what is pi over 2? Well, 3 pi over, or pi over 6. So 3 times pi over 6 is pi over 2. So the pi over 6 angle right here gives us a height of 1, which gets us out to here when theta equals pi over 6. If theta equals pi over 6, we get out to that max distance, don't we, of 1? Okay, so if you remember, we did kind of this, and then like how far out do you get? We get a max distance of 1 away. Anyway, and then when I come back down to here, so that's getting up to here, and then when I come back down to there, I'm going to come around here again, and I'll get back here. So that's why we go from 0 to halfway, pi over 3. So if you were not sure if you had a chance to read this stuff or not, I know you got, like, I'm not the only thing you got going, but dang it. Anyway, that's the biggest question is, man, quit moving that around. That's the biggest question is, you know, what do we put in for the limits of integration there? But that's why you stop at pi over 3, because that gives you one complete leaf. The other thing, like I said, that the book doesn't do a very good job on is saying, hey, what's the area? Well, the area, you don't need your function there. There's no, you know, you're on the table surface. So you're not putting in the f of r theta times RD theta, because that actually goes vertical and gives you a volume on that thing, right? So like if I had a surface sheet up here, I went 3 dimensions up, and then I wanted, you know, this volume that looks like a leaf type thing, you know, around here the whole way, then that's a different formula. Then I would put my F in right here. Okay. Now they're going to keep going here. So taking the antiderivative of R, that's R squared over 2, right? Plugging in sine of 3 theta there. So it's sine squared 3 theta over 3, right? And then I'm going to take the antiderivative of that with respect to theta. And of course, the antiderivative of sine squared, we had our tools. So once again, some awkward trig stuff. We use double angle formula. Remember that double angle formula? I said we want to remember those double angle formulas for calculating trig-based integrals. And so they end up giving you, you know, what it is in the example. I'm not going to work through that because I would have to go back and look it up just like you would on how to do a antiderivative of that. Okay, so let's try one that we can actually handle without having to look up chapter 9 and 10 stuff, and that's example 5. So we're going to do this one together as well. But it says just evaluate the double integral, and it's got the double integral over region R of e to the minus quantity x squared plus y squared, and then dA, and then bounded by certain things. And in this case, we're bounding it in the first, region R is in the first quadrant, bounded by the circle x squared plus y squared equals a squared. So that's a circle, right? And the coordinate axes. Okay, so we're in the first quadrant. Here's x, here's y, here's a circle, right? And then, so the biggest circle is, this is bounded. Okay, so this is the biggest one, right? So we're in quadrant 1 here, bounded by the circle. And what happens is I'm completely inside of here. So the x equals a, excuse me, out a, up a, left a, down a, that's the circle, right? That goes all the way around, but I want to be in quadrant 1. So I can have any radius. So my radius R, what color was I using? My radius R away from the origin could be anything up to that. It could be small, like down in here. It could be, you know, half of A, which is right here, can go out to A. So if A is 10, that's the biggest radius I got, if that makes sense. So that we're going to utilize that once again, instead of dA, what do we have? You know, well, if we're going to use polar coordinates here, I want to use r dr d theta. But then again, I don't have polar coordinates here, do I? I have x squared plus y squared. But what does that equal in polar coordinates? That equals r squared in polar coordinates, right? So I'm going to have the double integral of e to the minus r squared, and then r dr d theta. And then now if I want to look at this and say, hey, I want to do the r parts first, what does the radius go from? Well, the radius r goes from 0 over to A. So this is my radius r, how far out I am, right? And then theta is what angles I go from. So I'm going to go from 0 to A. Does that make sense?
Yeah.
I think it's okay. Once again, to me, the biggest challenge that you two are going to have is, hey, what are my limits of integration here, right? Anyway, and then so I've got that, and then now I'm going to switch colors up. I'll use purple here, or plum. Now I want to go d theta. So whatever that answer is in red, now I'm going to want to take the antiderivative with respect to theta. Well, where does theta go from? My theta starts here, which is theta equals what? 0, right? All the way up here to theta, this theta would be pi over 2, right? It's moving this stuff, like stop it. Anyway, so pi over 2 here. So 0 to pi over 2 for this outer one. And that's what they have, right? So then of course, I don't need to step through all this, but how would you do the one in red? Let's just talk about it. So they have the example. But to do this, well, the antiderivative of e to the x is e to the x, right? So that's not too bad. But the problem is, if I'm doing this part first, what I might do is say, hey, that's a power. So I might let u equal minus r squared, and then du equals minus 2r dr, right? Remember that? And then I've got, or you could let it equal positive u squared. Maybe I want to let it positive u squared. And then 2r dr, but I got, hey, r dr is right here. And what could I replace that with? I can replace that with du over 2, right? And instead of e to the minus r squared, if I just let u equal r positive r squared, it's e to the minus u times du over 2. So then that's, you know, bring out the, so that red part is 1/2 antiderivative of e to the minus u du. That's easy to do because this equals minus 1/2. The antiderivative of e to the u is e to the u. But then because I got that minus up there, then I have another minus out here. And then I could back substitute that back, right? So instead of u, what do I have? U is r squared. So it's minus 1/2 e to the r squared. Evaluated from what to what? From 0 to A. And that's where they get that. Did I forget a minus sign? Minus u.
Yeah, it should have been minus u. Yeah.
I forgot a minus sign. Anyway, so I'm running. I just don't have enough room on this board. I'm just going to clear that off. But anyway, they end up getting then for the red e to the minus a squared minus e to the 0. Of course, what's e to the 0 is 1, right? So they have antiderivative then of e to the minus a squared minus 1, and then they're going to take the antiderivative of that with respect to theta. So just real quick, what they have in red, I would have to verify this minus sign here. Just I think, like I said, I think I kind of messed that up just trying to do it quick. But taking this antiderivative with respect to theta, then is this is a constant, right? So basically it's just that thing times theta, right? And then evaluated from what to what, 0 pi over 2, right? So they plug that in. Anyway, getting all that, that's one we should end up. But anyway, they get pi over 4 because we had a -1/2 out there somewhere. Anyway, and then they come up with the answer of pi over 4 times 1 minus e to the minus a squared. All right, so anyway, that should pretty much take care of that example. Any questions so far? Now we're mostly through page 1107.
Nope.
Okay.
I'm good.
Perfect. All right. So you can see it's similar stuff to what we did in 13.2, but it's just different because it's polar coordinates. So I mean that's really the main thing there. Okay, and this is on page 1088. But anyway, it's just asking us to evaluate the iterated integral. And if I go integral from 1 to 2, and then integral from 0 to 2x of xy cubed dy dx. Okay, so the reality is just letting your eyes see this correctly is I'm going to do this one first, right? So they're not going to do that for you. Like we don't normally put those red brackets in there. But we're taking the antiderivative with respect to y, right? Well, where's the y variable? It's right there. So what's x? X is like a constant, right? So if I'm going to do this, it's just going to become xy to the fourth over 4, right? And then I'm going to evaluate that from 0 to 2x. So that's what's in the brackets because x is a constant. Pretty simple, right? You're supposed to say yes. You still hear me?
Yeah.
Yes.
Where do I plug the 2x in? What do I plug it in for?
Why?
Because I was curious. Oh, no. Oh, yeah. Y. Yes. So x times 2x quantity to the fourth. I know, it was funny. I must be delayed on my
Did you think we were
sound.
just saying why?
No, I was teasing you.
Oh, okay.
All right. Anyway, so it's a math geek joke. Anyway, and then if I plug in 0 for that y, I'm going to get 0, right? But anyway, 2 to the fourth is what? 2 cubed is 8, so 16. X to the fourth times x. What does that equal? This is 16x to the fourth. Divide that by 4, and we get 4x to the fourth times x. So it's 4x to the fifth. Correct? Is what's in the bracket. That's the red. That's this part. Correct? And then now I'm taking the antiderivative of that with respect to x, evaluated from 1 to 2. And so doing that is going to be, what, 4x to the sixth over 6, evaluated from 1 to 2. And then plugging that in, of course, I'm going to plug it in for x, right? 4 times 2 to the 6, 2 to the 6, 64. I'm just going to keep, instead of 4/6, I'm going to call that 2/3. I'm going to keep that out front. And then it's just 2 to the 6th power is 64 minus 1 to the 6th power is 1, right? So that ends up being 63 in there, divided by 3 is 21. So 2 times 21 is 42. So it's going to be 42. Should be the answer. Is that the answer in the back? I haven't even checked. Was it this 13.2? But you can see how easy calculus is when they give you simple examples, right? Calc 3. 13.2, number 21. What do you know? They get 42 in the book. That's what I got. I like it. I actually have a mistake in my answer key. Not for the answer, but for how they got to the answer. All right, all good? So that ought to help you do 22, right? Any question? I just want to make sure that you're good on this one.
Nope, that was pretty easy. Thank you.
Yeah,
Right.
that was.
You bet. Okay. So everything's easy if we know what we're doing. Do you want to do a tougher one like number 25? Just see if we can. Or do you want me to move on?
I don't really care.
I'm good.
You're good? All right. Trying to think if Okay, let's go back to why they're using a theorem on that, which I didn't really make you do. Oh, 13.2. I didn't really go area between the curves, did we? I didn't do that because I got kind of stuck on you. So I do need to back up on 13.2. I was thinking I was done. Whoops. Clear it off. But let's go back. So yeah, and that kind of goes back to what we were doing today, but where it wasn't real clear. But we're in 3 dimensions, right? But if we're only looking on a table surface, right? We're looking on the table surface, the X and Y axis, and we have area in between. Let me see. We could look at area in between curves. So if I've got these curves here and I want the area in between, the question is, what would that be? The area could be considered the double integral over region R of dx dy, or basically dA, right? And then that dA we could either write as dx dy in rectangular or dy dx, depending on which one you want to do first, right? And so really there is no F in there. Remember when we put the F in there, that ends up being like volume because we give a height to it and it makes it 3-dimensional, right? So I didn't really cover that, but what we can do is, take tiny changes, like let's say I want to do the dx dy. I can do like tiny changes here, there, and then look at a kind of a tall, skinny rectangle here. Anyway, so let's just do an example. Let's look at example 7, page 1087, and then if you want, I'll leave it up to you whether we do an odd exercise or not. Okay, so this is example 7. It says to find by double integration the area of the region in the xy plane bounded by the curves y equals x squared and y equals 4x minus x squared. Okay. Well, we know what those pictures look like, right? In fact, they have a nice picture of it for us, so we don't. But y equals x squared, boom, is right there. Y equals 4x minus x squared actually goes through the origin, so that one's in blue. Anyway, the other one, no, it's kind of before it starts. Well, I didn't change my color, but anyway, that goes through the origin as well. Anyway, we're looking for this right here. Well, we have methods of upper minus lower, right? Area underneath the curve from back in Calc 1. So in Calc 1, section 4.7, we had ways to come up with that area, but they're asking us to do that with double integrals. Sorry, this is kind of how I meant to draw this one. There's that one there. And so the reality is the area, excuse me, yeah, let's just go back to black for the area in between. So the area is going to be the double integral of 1 dA, okay, over the region R. And then the question is, so what is that? Well, dA, we can do one of two ways. We can do it dx dy, or we can do it dy dx. Okay. And so the question is, you may default to wanting to do it this way, right? Dy dx. Right? Like if you didn't know any better, you're like, hey, I'm just gonna do this one first. Okay. So what are we really doing first? We're doing the dx part. And the question is, what does x range from? Well, it ranges from 0 to something, right? So this from 0 to whatever. So this is x1 equals 0. What's x2 equal? Well, that's kind of a good question, isn't it? So the reality is this one, what's x equal? X equals plus or minus square root of y, right? If I wanted to solve it for x and make this a function of y, right? It'd be, on the top one is that, right? But what about this one? What if can you solve this for x? This is tough to solve for x, right? So we can't solve this one for x. So that makes this version having the x inside of there first a little tough. So we really don't want this one. We're going to want that one. And if I want that one, let's go back and change it. By the way, is it easy to? Yeah. All right. Maybe it's easy. I don't know. We'll find out if it's easy. But anyway, so if I'm going to take the double integral and then with respect to y, then with respect to x, of course that's a 1 there. What do my y's range from? Well, when I look at that picture, which one is on the bottom? That's the y equals x squared, right? Is on them. And which one's on top is the y equals 4x minus x squared, right? So what do the y's range from? They range from the bottom one to the top. So really what we're going to do is we're going to take these tiny changes here, I believe. Is that how we're doing that? I don't know. Anyway, the bottom one is x squared and go up to 4x minus x squared. Am I doing that right? I don't think I'm describing that right, because the x's, so I will do this first, but then I'm going to iterate that among the x's. So if I've got this, and then I'm going to go x's from here to here, right? So x1 is 0 to x2 over here, and so I'm gonna iterate that from the left one to the right one. I don't know. It looks good to me. Like I said, what I say the toughest part of these sections are going to be figuring out your limits of integration. So I don't think I'm doing a very good job explaining this. But what would X run to? Where do these intersect? Could you figure out?
Yeah.
So you'd have x squared equals 4x minus x squared. Is that right? 2x squared minus 4x equals 0, which divide by 2, so it's x, 2x times what? X minus 2 equals 0. So what is x? X goes from 0
To 2. Yeah.
to 2, okay, for the x's after that. But anyway, this one right here, what is y? So the reason we want y on the inside is because we've already solved for y in terms of x. So really this is like, you know, f of x to g of x right here. Excuse me. Yeah, f of x to g of x right there. All right. And then, so with that being said, taking the antiderivative of y is going to be y, so this part in here is going to be y evaluated from what? X squared to 4x minus x squared. Plug these two in. So it's 4x minus x squared, and then minus, the bottom one is x squared. Plugging those in, and it's 4x minus 2x squared is what I get in there. And then I'm going to take the antiderivative of this from 0 to 2, right? So taking the antiderivative of that from 0 to 2 with respect to x, and see if that works out. So that's going to end up being, I'm just going to come right here, 4x squared over 2 minus 2x cubed over 3. So that's 2 and 1. Evaluated from 0 to 2. So plugging in 0 is going to be 0, but plugging in 2, that'll be 8 minus 16 thirds, right? Which is 24 thirds minus 16 thirds is 8 thirds square units, which is what they got. Okay, as far as area of the region. All right, so anyway, I did want to cover that. So very similarly to what I was doing in polar coordinates, they didn't do a very good job in either section of describing that, but they actually showed it on page 1087 in 13.2. I just hadn't covered it because I got cut off on my technology, but that the area is the double integral of the region. But because we can't solve y equals 4x minus x squared for x, we're not going to want to use the dx dy one on that one. It's going to be easier to use this one. So hopefully that makes sense to you. And I don't know if I had you do an area one or not. I did the approximate area. I don't think I did that. So anyway, okay. Can I move on now? Or did you change your mind, not want me to move on? Triple integrals, let me cover that real quick. So what is a triple integral? Would be very similar. So section 13.5, I'm not going to take a lot of time on this, but this is triple integral over region R. So R is going to be, excuse me, not region R. It's a over S. They call it S. And so region S, we've got 6 planes kind of making a box. So that's kind of like a rectangular box, the surface S. But anyway, so triple integral of f of x, y, z. Now we're in 3 variables now, and then dv. Okay, so dv, if I'm in rectangular coordinates, can be dx, dy, dz. Okay, and or a lot more common is doing backwards, dz, dy, dx. But the reality is we could have dy, dx, dz, or we could have dy, dz, dx. And I'm missing one of them. I could have dz, dx, dy, dz, dx, dy. Doesn't really matter how you split it up, or dx, dz, dy. So you could have all these different options there, right? But anyway, that one might be one of the more common ones. They do that at the bottom of page 1111. Anyway, so basically what we're looking at is they use A1 to A2, things like that. But the reality is if I've got my function here, f of x, y, z, if I'm doing dz first, then what do I got? I've got from z1 to z2. Now, what is z1? You got to think about that. What is z1? Z1 is a function, right, of two variables. So this could be, they use different symbols, but we might call it phi of xy. And this might be, so phi 1 of xy, this might be phi 2 of xy. So so z is defined in terms of x and y. And then if I go to the next one, I say, okay, now I want dy next. Well, really we're y1 to y2. But what's y? Y is a function, we might call it theta of x. So theta 1 of x to theta 2 of x. And really we could use any variable here. But y is going to be some function of x, right? And then we get, last but not least, we go to the dx. X is going to be from x1 to x2. Well, that's just in terms of x, right? So we're good there. So the reality is, you know, the one on the inside, you know, you've got it defined in terms of the other variables. I think that's the key. So that was kind of what we ran into on that example 7 that I did in the previous section. And then of course here I've also got, you know, I got to do it twice. I got to step it down each way. But that's really a triple integral. The nice thing is, and of course, whoa, where'd that come from? We're looking at like a rectangular box, 3-dimensional rectangular box, which kind of easy to draw that way, kind of. That's what we're looking. This is surface S, or not surface, but it's a volume. Really, it's a dV. So this is dV. So we're splitting this up into tiny rectangular boxes is what we're doing on that. And then if I have, just so you know, similar to before, like the area, where'd that go? Before we had the area was the double integral over region R of 1 dA. That was the area. Well, we're going to have the volume is the triple integral over shape S of 1 dV. So that's an S. I don't know. I use a cursive S there, so it doesn't look like a double integral. But this is kind of a nice thing there too. Of course, what did we have in 2 dimensions? We had volume. What did we say? If F is entirely on or above the x-axis, or above the table surface, we could have f of x, y, and then dA, which is either dx, dy, or dy, dx, right? Anyway, so we have that as well for volume, but that's a double integral. This is a triple integral formula where we have the 1 in there. Okay, so the area, so these are very similar on how they look in the different dimensions. Okay, now what does it mean if I put f of x, y, z dv with the triple integral. Well, now we're having trouble visualizing a physical representation of that, but we could certainly do it. Things of that nature. So let me just give you one example and try and make it a fairly easy one, hopefully. Clear it. Come on. All right. So let's just, maybe we could do, why don't we do number 2? Because I don't think you had to do, oh no, I don't want to do number 2. Let's start easy. Let's go number 1 or number 3. What do you want? You want number 3? Page 10, 11, 15. Number 3. We've got the triple integral of x plus y plus z dz dy dx. And then what we're doing is we've got a surface given by, I'm gonna do different colors first. We'll do red first. The z's go from 0 to x plus y. Okay, notice that z ranges from 0 to x plus y. So z is a function of x and y up here for both of them, actually. Z is a function of x and y. So we're going to figure this one out first. And then we're going to do y goes from 0 to x. So for the y, we're going to do that next. But y is a function of x. Both of these are functions of x. Right? Y is a function of x. And then, of course, last but not least, the the x's are left, and the x's are just going to range from 0 to 1. Okay, that would be that. So that would be the last thing I do. So let's do it in order. Start with the red. If I take the antiderivative of this with respect to z, everything else is a constant. So this will be xz plus yz, since x is a constant and y is a constant. And z is the variable, so plus z squared over 2. Hopefully that makes sense. And I'm going to evaluate that from what to what? 0 to x plus y. And of course, where do I plug these in? Everywhere there's a z, right? Okay, so let's do that first. I'm going to get, this could get a little awkward without much room to write, but x times x plus y times x plus y plus x plus y quantity squared all over 2, which I'm going to write that as x squared plus 2xy plus y squared all over 2. And then, of course, if I plug in 0 minus 0, right, we get that. I am going to rewrite this. This is x squared plus xy. And this is plus, and I'll put it, instead of yx, I'm going to write xy plus y squared. And anyway, so now I got x squared plus 1/2 x squared is 3/2 x squared. And then, wait a minute, plus another x squared. I didn't know I had that. Wait a minute, what? X squared plus xy. Where did that come from? Okay. Anyway, plus xy is plus 2xy, plus another xy is plus 3xy, I think. And then plus y squared plus 1/2 y squared is plus 3/2 y squared. So I believe this is what I have in the red. Anybody agree with that?
That's what I have too.
Okay. So did you write it down? You were working it on your own?
Yeah, as long as your integration is right. I didn't do that. I just took yours. But in terms of simplifying, yeah.
Well, I'm just running out of room. So what I'm going to do is I'm going to rewrite it. So now I've got let's go back to black. double integral, and what did we say we had? We had 3/2 x squared plus 3xy plus 3/2 y squared, I believe, right? And then I still have to do dy. I can't remember if that was blue or what. I think it was. And this is from 0 to x, right? So I got to do that next, where y is a function of x. And then last but not least, I'll do the dx, which that goes from 0 to 1. Okay, so what's my variable here? Coming back, doing what's in here. My variable is the y. Everything else is a constant. So this becomes 3/2 x squared and then times y, plus y is the variable, so it's 3x y squared over 2, plus 3/2 y cubed over 3. What's nice is those 3's cancel. And I'm evaluating this from 0 to x. And once again, I'm putting it in everywhere there's a y. So what's that part? So plugging in the x here, everywhere there's a y. Then I'm going to get 3/2 x cubed plus 3x y cubed over 2. Excuse me, no, 3x times x squared is x cubed. You know what I meant, hopefully. Plus x cubed over 2. And then that looks like they're all x cubed. So I got 1.5 of them. Another 1.5 of them is 3 of them. And another half is 3.5 of them. So I believe that's 3.5 is 7/2 x cubed, I believe. And that's what I should have for this part. Hopefully. All in favor? We're going to find out real quick. So now it's the last one is going from 0 to 1 of 7/2. Of course, I could pull that 7/2 out, right? But it was x cubed, I think, with respect to x. And so it's 7/2 x. I'm just going to pull that out front here. Anyway, x to the 4th over 4 evaluated from 0 to 1. So it's going to be 7/2 times, plugging in 1, it's 1/4 minus 0. So that would be 7/8 should be the answer. Hopefully that works out. Anybody cheat and look at the answer? Hey, number 3 is 7/8. What do you know? Then the book is correct. Because I know I am, sister and brother. All right. Anyway, so you can see it's the same thing, just just a little bit more involved. The biggest thing is when we have those, if I've got z first, if I have triple integral and I've got z first, then this is z equals f1 z1 is some function in terms of x and y. So this is like z2. But anyway, so you're going to see x's and y's here possibly, unless it equals a constant like 0, which makes life easier, right? And then same thing with the y's. The y is going to, y1 is f sub 1 evaluated at x or whatever, some other function. Maybe I should have called it g. Y2 is going to be g2 in terms of x. So you're going to see potentially x's in the limits here if dy was next. And then, of course, then when you get to the last one, then that's just going to be a constant x1 to x2, whatever those, hopefully, theoretically numbers.